Thank you very much, and I'd like to thank organizers for inviting me to speak at this wonderful conference. So this is a work done with Nima Kanihamet and Johannes Henn, and there is some related work with the same people and Dimitri Chicherin, and also a separate work with my students Taro Bran, Umut Oktem, and our UC Davis postdoc Shruti Paraniape. Okay, so this talk will be about scattering amplitudes in planar n=4 super Young-Mills theory. We will use it as a playground for some new theoretical ideas. And in particular, I will use the Amplituhedron formulation for the loop integrand in the perturbation theory, which I will quickly review later, to do kind of a first attempt using this picture to perform an all-loop order resummation, and eventually also say something about the strong coupling physics. Something we have been trying to do for a long time. Now, in order to do it, I will define some IR finite quantity, which will be derived from the 4-point amplitude. It will be not directly the amplitude because it suffers from IR divergences, but it will be closely related object. And I will introduce some new expansion, which will be exact in the complete constant. So it will be not a perturbative expansion. Different type of expansion, which will be natural from the perspective of the Amplituhedron geometry. So it's something which we call loops of loops expansion, but you will see concretely what it means. And in the end, I will make some connection to the Cusp anomalous dimension, which controls the IR divergences in this theory. Okay, so an introduction. So we will be interested in amplitudes in planar, large, and limit of maximally supersymmetric Young-Mills theory in 4 dimensions. This theory enjoys a lot of symmetries in addition to a conformal symmetry of n=4 super Young-Mills. In the planar limit, there is also a new symmetry called dual conformal symmetry. It's another conformal symmetry acting in the dual space of momenta variables. And as a result of all that, the amplitudes are simpler than in gauge theories. They enjoy a lot of special properties, but it's also a good toy model, the theory, the amplitudes and the theory as a whole, for studying different aspects of gauge theory. Of course, there are certain simplifications, but at the level of amplitudes, for example, the 3-level amplitudes in this theory are the same as in QCD. At loops, of course, it's different. The amplitudes are UV finite, and the perturbative expansion is exact because it has a finite radius of convergence. There are no non-perturbative effects in the planar limit. We will be strictly working in the planar limit of this theory. However, the amplitudes are IR divergent, so in order to calculate amplitudes, we have to choose a regulator, and we have to break the conformal symmetry, for example, by choosing a dim reg. Okay, so let me quickly say a few things about the perturbative expansion. So that's a loop expansion, and to construct the L-loop scattering amplitudes, we can use various methods, including the standard Feynman diagrams, but nowadays we mostly use unitarity methods. The idea is to construct some basis of integrals, which you calculate you construct the basis and calculate the integrals once, and then in a particular theory, you fix the amplitude by fixing the coefficients in front of these integrals using cuts. And the cuts cut the amplitude, the loop amplitude in the product of 3-level amplitudes. So the coefficients are products and sums of products of 3-level amplitudes. And of course, once you have calculated the loop integrand in this way, you have to do the loop integration. And that's, in principle, that's a difficult task. And you use different methods to do the loop integration. Now, let's now work in the planar limit. In the planar limit, there is something special because the external particles, the external lines are ordered. So you can define global variables called dual variables. And you can not only talk about the individual diagrams, individual Feynman integrals, or these integrals in the basis, but you can label them all in the same way, and you can sum them together. So you can define something. You can define a unique rational function called loop integrand at L loops, which is basically summing all contributions together and just talking about this function. Now, the dual variables are derived from the momenta because the particles are ordered. So you also have ordered momentas. And there are these points x, which are related to the differences of the momenta. And these are the dual coordinates. And also you can derive another set of variables which are useful, called momentum twisters. And the external data are then labeled by points in this momentum twister space, which is just projective space P3. Now, this is for the external momenta. For the loop momenta, you, instead of traditional L, you can also use the points in the dual space or in the momentum twister space. The loop momenta are labeled by a line. So this is basically just change of coordinates, which is convenient to use for planar amplitudes. Now, once we summed everything together, we have this loop integrand, and we can basically forget that it came from a sum of Feynman diagrams or anything else, and just think about it as a unique rational function that you can construct in a different way. Yeah. The function satisfies all cuts that any amplitude should satisfy. In planar n equals 4, it has also this dual conformal symmetry, and you can then use some other method how to construct it, for example, using recursion relations from the lower point and lower loop amplitudes. Now, the building blocks then that show up in these recursion relations or in these other methods, one of the set of building blocks that you can use are some gauge invariant functions called on-shell diagrams, which are just product of 3-point amplitudes. In these recursion relations, you can always recurse all the way down to the simplest objects in the theory, which for this theory are just 3-point amplitudes. So once you recurse everything down, the building blocks for the amplitudes that you get are pictures like that, which are products of 3-point on-shell amplitudes. And there is also a dual formulation for these objects when instead of using this physics picture, you can also use mathematical pictures when for each of these graphs, you construct a Grassmannian matrix and then you reconstruct these objects using a certain differential form on the cell in the positive Grassmannian. Anyway, I will not talk about it in more details, but in this picture, once you eventually glue together all these objects, once you take the sum of them, you get the Amplituhedron construction we will use later here. Now, let me also mention that this is basically reformulating the perturbation theory, but there are also other methods people have been using in recent years, which basically skip this standard framework of constructing the integrand, integrating things loop by loop. The first method are bootstrap methods in perturbation theory when you skip the integrand part, and instead of constructing the integrand, you directly try to construct the L-loop amplitude. And for that, you need to know what is the function space for the amplitude at L-loop order. And the important information or the invariant information about the functions is carried by an object called symbol, which encodes the branch cuts of functions which appear at L-loop order. And you make an ansatz for the symbol of the L-loop amplitude with certain entries. It's kind of a code which contains certain entries. These are symbol letters that corresponds to some cross ratios of kinematical variables. And then you impose some physical and mathematical conditions and fix this object completely. Yeah? So this is, for example, the symbol for certain two-loop amplitude. And then in the end, you have to also go from a symbol to actual function. So there are some more constraints that you have to impose and fix some constants which are not encoded by symbol. So this is another method which doesn't use the standard paradigm of integrand and integrating things. Now, in planar n equals 4, we have also an important relation between scattering amplitudes on one side and Wilson loops on the other side. This also explains when there is this hidden dual conformal symmetry of the amplitude, because this is just a conformal symmetry of the Wilson loop. And using this picture, many important results have been achieved. So in the original work by Aldai and Maldacena, the strong coupling limit of the scattering amplitudes have been calculated as a minimal surface in ADS using ADS-CFT correspondence. Also, In another program, the flux tube method at finite coupling, this is an expansion which is exact in coupling constant, but expands the amplitudes near the collinear limit. So in some special kinematics, near a special kinematics, exactly in the coupling constant, using some integrability input. So in the end, apart from the traditional perturbative expansion, which expands in small coupling constant, we also have this expansion, which is exact in G, but expands in special kinematics. In our case, in this talk, we will have another type of expansion, which is kind of complementary to both of them, which will be exact both in kinematics and in the coupling constant, but will expand in some other direction. Okay, but before going there, we will actually define the object we will be calculating, and this will be related to the logarithm of the amplitude, and which will lead to some IR finite objects that we can actually play with. So the dual conformal symmetry for planar n equals 4 amplitudes is extremely restrictive. So at 4 point and 5 point, it actually doesn't allow us to almost write anything. Basically fixes everything to all loops up to some constant factors. So if you resum if we sum the amplitudes when we define the usual Toft coupling, we will find that the full L loop, the full non-perturbative amplitude in this case exponentiates just from the one loop amplitude. When this product together contains the leading 1 over epsilon square divergence, and then it continues. So the only unknown functions is this f function and the c functions, which don't depend on any kinematical factors. Yeah, the only thing which depends on the kinematics is the one loop amplitude, which exponentiates. Starting at 6 point, there are more kinematical functions you can write. The dual conformal symmetry allows you to write certain cross ratios, and there are additional functions that you can write and that indeed appear in the full amplitude. And this is called remainder function. Now, if you take the logarithm of both sides of this equation, you will find that in epsilon expansion, in the dimensional regularization, the leading divergence just scales like 1 over epsilon squared. There is some factor which depends on the coupling constant, and then there are some subleading. But here there is a very mild divergence for the logarithm of the amplitude thanks to this exponentiation. While the L loop amplitude will diverge maximally as 1 over epsilon to the 2L, yeah, which have much stronger divergence. Okay, so now let's look at this logarithm of the amplitude, because that's a very mildly divergent function, and we will actually turn it into some IR finite function. So I can start with just taking the logarithm of the full perturbative series and just expand in small g, and I get a one loop logarithm, which is just one loop amplitude. I get a two loop, three loop, and so on. And you can see that these are just combinations of amplitudes and the products of lower loop amplitudes. So, for example, in this case, you have three terms at three loops. Each of these terms is maximally divergent as 1 over epsilon to the 6, while this combination is only divergent as 1 over epsilon square. So there is a huge cancellation of IR divergences in this particular combination. Now, this is for amplitudes, but because we already know that in the planar limit, we can talk about integrands. There is a well-defined function. We can actually also construct an integrand for the logarithm of the amplitude, rather than for the amplitude itself, which is just combining the pieces which show up in this expansion for the logarithm. Now, this integrand is a rational function. It looks like an integrand for the amplitude, but it's actually an integrand for the logarithm. It consists of these combinations of amplitudes. And the cut structure of this integrand function encodes the very mild IR divergence of this object at any loop order. At any loop order, it will only diverge mildly as 1 over epsilon square. Okay, now once we constructed this integrand, we can integrate it. So we start with the L loop object, which here I use this momentum twister notation, will depend on L loop momenta or L lines in momentum twister space. That's just a matter of using some kinematical variables. And now I'm integrating it, and at each step I will integrate out one of the loop momenta, but everything stays IR finite until the last step, when it generates the IR divergence. Okay, so the object that we will study here is the last object before we turn it into an IR divergent logarithm of the amplitude, which also in the literature is called F. It will be L loop object, which only depends on one loop variable and external momenta. And actually, dual conformal symmetry tells us that it only can depend on one cross ratio Z. So at L loop, it's a function of just a single variable Z. And because this is a finite function, I can just write a formal sum and resum to all loops. So we get our function that we would like to work with, which is F, depends on G and Z, depends on the coupling constant and one cross ratio. And it is related to Wilson loops because it appeared in the literature earlier as a ratio of two null polygonal Wilson loops. One with the Lagrangian insertions. So one has an extra point, x naught. This is written in these dual variables. It can be easily rewritten back to the momentum twisters. This ratio is basically essentially the function that we just defined using the logarithm of the amplitude up to some rescaling. At weak coupling, this function has been calculated from this Wilson loop size to several orders. It's an expansion in G square at low coupling, in the Toft coupling, and at strong coupling using ADS-CFT, it's an expansion in 1 over G when the leading term goes like G at strong coupling, and then there is a subleading term which is constant, sub-subleading which is 1 over G, and so on. So we have this information about this function at both weak and strong coupling from different perspectives. Now, as I said, after we integrate this function, we would recover the logarithm of the amplitude, and that is divergent. But the IR divergence, the leading IR divergent, is controlled by the Cusp anomalous dimension, which is just a function of G. And this is known exactly from integrability. There is an exact formula that you can expand at weak coupling, strong coupling. You have a complete control over this function of a coupling. And additionally, there is a way how to extract this gamma cusp from this function f that I just defined. Yeah, there is some formula. It comes from it's mostly dominated by some singular region of this function, but there is a definite way how to extract gamma cusp from this function f. So our goal will be to focus on this function f, and motivated by the Amplituhedron picture, we find a new expansion. This expansion will be exact in G and Z, but we'll organize the contributions differently based on the number of loops in the loop space. And we will be mainly interested in the strong coupling limit, which is something which so far we couldn't access using our weak coupling methods that we've been doing before. Now, our simplest case we will study will be somewhat analogous to a resummation that was done just at the level of Feynman diagrams by these people, which is just summing ladder integrals and for off-shell external legs. So these are IR and UV finite integrals, and it was just resummed and expanded in strong coupling, and it was found that at strong coupling it's exponentially small. So it scales like e to the minus g, this sum. So we will see what we get if we get something similar, or if we can get closer to the correct linear grow at strong coupling G, which is predicted by ADS-CFT. So let me quickly say something about the negative Amplituhedron geometry. So let's start with the positive geometry. This was something which was nicely reviewed in the talk in the morning. So for our purpose, we just think about some geometric space given by certain polynomials in some parameters which parameterize the kinematics and define some region. And on that region, we define a canonical differential form, which, for the purpose of n equals 4 super Young-Mills, has a special property that it has a logarithmic singularities on the boundaries. And this captures, by this Amplituhedron picture, all three-level amplitudes and loop integrands. Now, the case that we will be interested in is a 4-point Amplituhedron. So there are L lines, L loops representing the loop momenta. Each line is parameterized by 4 parameters, and there are certain conditions that the Amplituhedron picture gives us to what is the parametric space for these parameters. Yeah. And the canonical form on this space, on this geometry, reproduces the 4-point L-loop integrand. Now, in the graphical notations we will be using, for each vertex, this is a loop, we use a dot, and the blue dashed link is a positivity condition. So if I draw a picture like that, this is exactly what gives us the geometry, the Amplituhedron geometry for the L-loop integrand. But there can be some other geometry, which is a perfectly fine geometric space with its own differential form, which is not an amplitude, but the Amplituhedron, which reproduces the L-loop integrand, corresponds to a completely connected graph. Now, we replace the positive link by the negative link. Instead of positivity conditions, we will have negativity conditions, because if we take a union, we get no conditions between two different dots. And this is just a graph theory exercise that instead of one complete graph with these links, we get a sum over all graphs with the negative links. Okay? And this was, each point here is a loop. It's a one loop momentum. So we can now sum over all loops, and this formula actually exponentiates, and we get a sum over all connected graph here. So here there is a sum over all graphs, here there is a sum of over all connected graphs in the exponent. And we take a logarithm of both sides, the exponent on the right-hand side cancels, and the L-loop logarithm can be written as a sum of differential forms over positive geometries, which are represented by these graphs, when each link corresponds to certain inequality. Now, if we integrate the differential forms here, we get each of the term will be 1 over epsilon squared divergent after integration. Now, from the properties of this integration, as I showed, if we freeze one of the loops and integrate over the others, this object is IR finite. So this is an expansion for this function f that I defined before in terms of IR finite objects. Okay, so now we can do the integrals at, if we have no loop to integrate. So this is a frozen loop. This one we don't integrate, we just get one. At one loop we get some function. And at two loops we get 3 different graphs which contribute. And despite this is all 2 loop pieces, you see that these 2 geometries gives much simpler results than this geometry, which has some loop in this loop space. They are both the same loop order from the conventional purposes, but from the purposes of these geometries, this one is more complicated, and you can actually see it at the actual expression. So this is a simple tree geometry, and this is a more complicated one-loop geometry. So to determine the integrand and then integrate to an arbitrary geometry, which we need to get the full control over this function f, is complicated. So we can do some approximation. We initially can approximate this f by picking special geometries, which are only ladder-like geometries. Yeah, they just look like this, and we ignore everything else. And using a differential equation method, we can actually determine what is this function completely to all loop orders. Okay, so we use some differential equation method and we write an exact expression for this function, which is certain approximation of this function f. But if we go to a strong coupling, we see that it's exponentially decreasing, similar to what happened with this resummation of the ladder integrals. So this is not a very good approximation, yeah, because the exact result in strong coupling grows with g. Okay, we can do a little better because we also get a full control over all 3 graphs, 3 negative geometries. And this is a weak coupling expansion, and then we get more and more, but we can calculate all of them and use also similar differential equations methods, and also determine this function f completely for any values g and z. It's a little bit more complicated function. It depends on some a, which is given by this formula. We cannot solve analytically for that, but we have the result, and we can expand at weak and strong coupling. Especially for us, it's interesting to expand at strong coupling, and we will see that at strong coupling we get a constant term in G, but we get a 1 over G expansion. Exactly what happens for the exact function f. So in comparison, we are missing the leading piece. However, we are getting the 1 over G expansion, so we are getting closer to the actual result. So in this tree approximation, we reconstructed this 1 over G expansion. Now, surprisingly, if we look at gamma cusp, which I said can be derived from this F function, at strong coupling, this is an expansion of the exact formula obtained by these people. And this is a result obtained by our geometric approximation, and it has a leading term in G. So actually, not for the function F, but for the gamma cusp, we actually also get linear grow in G at strong coupling with a different coefficient. So the other terms are also important, the ones that we didn't consider, the 1 loop, 2 loop, 3 loop, and other geometries. But for the gamma cusp, we are actually getting qualitatively the right behavior at strong coupling. Okay, so let me just quickly go. We use this function, we define this function f, and define this new geometric expansion, which is exact in G and Z, but it kind of expands the amplitude, or this object derived from amplitude, in this new way, which is closely related to geometry, but doesn't have any physical interpretation, at least at the moment. Yeah, what it means physically to ignore certain graphs and say that the others are important. And we extracted gamma cusp and got surprisingly good behavior. Not the exact match, of course, because we ignore many other terms, but surprisingly good qualitative behavior and strong coupling. So the main question here is, how do we reconstruct back the leading G expansion and the strong coupling? If we can do it just including more geometries, or in principle we have to include all of them, otherwise this behavior will not show up. And there are also some other open questions, including some deformations that we can do on the geometry, and more precise relations to integrability. And perhaps the most complicated question is, we are still working in the perturbation theory, despite we are able to resum. The question is, can we define the geometry, or can we directly go to the strong coupling and define the geometry there and see some emergence of strings? Thank you very much.
Thank you. Are there questions? What was it? You will go back a few slides.
Here.
Yeah. Okay. Right. Is there any way one could come up with a differential equation, or translate the differential equations between those two?
Well, we can, but we don't have the exact formula for the gamma cusp. It's just this approximation using this special set of these negative geometries. Yeah, so for them, yes. So for them, you can also write a differential equation. But not for the full gamma cusp. Yeah, for that you need a complete control over basically the full L loop amplitude to all loops to do that. Yeah, which is something exponentially hard at the moment.
Further questions? So let's thank the speaker again.